Finally, grade 12s, it is your time. I know that you've all been sitting there waiting from grade 10, so it's been a good 2 hours so far,
It has
Bruce.
been a long time, eh?
Yeah, I'm telling you. But today, we've got some exciting things we're going to go through, and you know what? Let's speak to the master himself. He's going to tell us.
Right, guys, we're actually doing some physics tonight. We're going to be looking at work and energy. So grab your notes. What are you doing?
Yeah, I'm getting full of
Is
energy.
that the work?
This is
that's
energy, the work and energy.
Okay, Leanna's on her own little mission at the moment. But guys, grab your notes, grab your exercises and things like that. I'm going to be going over the basic concepts of work and energy with you, doing a couple of examples on the board, hopefully making things a bit clearer.
Fantastic. So guys, get chatting to us on Facebook. That's facebook.com/learnextra. Also chat to us on Twitter. Our handle is @learnextra. My name's Indiana and I'm chatting to you. If there's anything that you don't understand, even if Bruce is going too fast, using funny colored pen, tell me. But most of all, guys, let's try and stick to the topic at hand so we can get all of the questions answered and get through it nice and slowly and through a good pace. So let's take a break, get those questions in, and we'll see you now. Welcome back, grade 12s. Finally, it's your part of the day. I know that you all are so excited. You guys are all screaming, yay, work and energy. Bruce, they're very excited. So I think what we're going to do, first of all, get those questions in, guys. Let's get them coming in. Bruce, over to you.
Right, Indiana, thanks very much. And guys, I must apologize to start. I've had a little bit of a cold and my throat's a little bit sensitive. So I think my voice might be sort of going a little bit up and down. So I do apologize
girly today, hey?
I'm sorry?
A little bit girly.
A little bit girly. It might be sort of going like this, but guys, that's what happens when the early winter season is starting, even though some people still think it's the height of summer. But guys, we're going to talk more about work and energy today rather than about biohealth. Guys, important thing, big section of mechanics, especially in the grade 12 exam, guarantee the question somewhere along the line on work and energy. And what we've got to do today, guys, is make sure that we knuckle down those basics of work and energy. There's nothing more important than making sure that we've got the basics, the foundation settled, because then it doesn't matter how complicated the problem actually looks like and how it becomes and how the examiner tries to sort of confuse you. As long as you've got your basics in place, then there's absolutely no problem. So guys, what I'm going to do is go through a couple of the initial foundation concepts, make sure that we understand them, do a couple of problems with you. Indiana's going to have all the questions. She'll fire them to me when she's got a couple in, and then we can discuss it and we can have a chat, and just to make sure that we do understand. Okay, so guys, without any further ado, under the heading of work and energy, what are we going to have a look at? Well, guys, the word work is something that we use pretty much in everyday life, don't we? We talk about homework, and we talk about people really working hard. And does that actually mean a physical work or mechanical work like we talk about in physics? Well, not all the time. It doesn't really mean that. However, there's one common thread that actually runs through it. And that is, whenever we do work, whether we are working hard on the sports field or doing a lot of homework, we have to put in an effort. Okay. Now, how does effort translate into mechanics, into physics? Well, an effort is always described through what is known as a force. So guys, when we do work, we have to have a force involved. So what I'm going to do is I'm going to draw an object on a flat surface, okay? And that object is going to have a certain mass, which I'm going to call m at this stage. And what I'm going to do is I'm going to show now an effort force, all right? And I'm going to make the force move to the right-hand side, and I'm going to call that my applied force. So APP standing for my applied force. Now guys, what's going to happen if I'm on that surface, and I'm going to assume a frictionless surface at this stage? There's no friction at all. We'll talk about friction a little bit later. If I apply a force on a frictionless surface, then what's going to happen? Well, that object is obviously going to move. And I'll just draw it in a dotted line like that. And it's going to end up in a position over here somewhere. So in other words, that applied force has caused the object to undergo a displacement, which I'm going to call delta x. Now, when we have a combination of applied force and that applied force causing that object to move, then we have work done in the system. And that's very important, guys. So my work done must be equal to the applied force multiplied by the displacement. Okay, I'm just going to squeeze that in there. Sorry guys, I had to squeeze that in a little bit. Okay, so what's my work equal to? It's equal to my applied force multiplied by my displacement. And there, guys, is our very simple little mathematical equation to allow us to calculate the amount of work done. However, there are a couple of important things. Let me just scroll down a bit. There are a couple of important things that we must remember when it comes down to work. Okay, and that is, work is only done if the force is parallel to the direction of movement. Okay. Work is only done if the force, and that's the applied force, sorry, let's just put that in there, and the applied force is parallel to the direction of movement. We have to make sure that we are always working with our force in the parallel to direction of movement. The second thing that we're going to have a look at is that work is only done if that object is moving. Okay, work is done only if object moves. Sorry, there we go. Only if the object moves. If the object does not move, excuse me, if the object does not move, if the object doesn't move, then we do not have any work being done. Okay. Now, the third thing that we must also be very aware of is that the force must constantly act on that object. So the force constantly acts on the object. Okay, right, so we've got three things we've got to keep into consideration. I'll just run through them again. The force must act parallel to the direction of movement of that object. Work is done only if the object moves. In other words, it covers that displacement. And thirdly, the force must constantly act on the object. If the force stops acting on the object, then the work will stop. Okay, and those are the three things we must take into consideration. Right, now, let's see how we can apply this now in a very simple type of calculation. So let's extend the page down a little bit. I think, in fact, what I'm going to do, let me get a new page up. That'll be the easiest.
Bruce, before we go on, I just got to say something, because I'm very passionate about mindset learning this page. Like,
right.
This page is my baby. Can you believe that we've actually just reached 6,000? Not only have we reached 6,000 mindsetters on the page during this lesson, we've got 6,028. So during today's lesson, we've literally gone up like 300 people. So mindsetters, thank you so much for watching. And Bruce, back to you.
Well, we're getting all the stats coming in, and the 6,000 people on the
it's incredible.
page.
It's incredible.
That's unbelievable. That must be one of the biggest sites around at the moment.
Yeah, especially in terms of education, guys. I don't think that there's anything out there like this at the moment. And not only is this platform for the learners, well, it's not only for us, it's for the learners to also use and to ask questions. And I see there's always the same guys that are answering questions. If somebody doesn't understand, sometimes I don't even need to even ask Bruce, because you guys are answering before. So that's fantastic, guys. Keep it up and well done.
Awesome. That's great, guys. Let's just get back to this. I want to do this problem quickly, and then we can probably take a couple of questions just to see how we are. Bit of a perception check. Right, so what I've got, I'm just going to redraw my diagram very simply. And I'm going to put an applied force. And I'm going to make that applied force 100 newtons to the right. Okay. So what happens now if that object is going to move a distance of 10 meters as a result of that applied force? Well, as we said, guys, our work done is going to be my applied force multiplied by my change in displacement, and all we have to do is simply plug in a nice simple problem, 100 newtons, which is my applied force, multiplied by my displacement, and we can very easily see that 1,000 joules of work is done. Now, I've introduced a unit which I want to have a little talk about. I've introduced the unit of work which is known as the joule. Now, if we look at this unit very carefully, and I'm going to take it from, whoops, let's get another color. I want to get, let's go back to red. If I look at force and I look at displacement, we know from grade 11, and even going back from those years, what the units of force and displacement are. Well, we know that the force is always measured in newtons, and I've actually used it up there already. And we know that displacement is equal to meters, and I used it over there. So if I say force times displacement, what am I actually saying? I'm actually saying newtons times meters, which we call the Newton meter.
Bruce?
Yeah.
Would you be able to change the color of your pen?
Really? Is the pen not,
Yeah.
is it not coming out all that well?
Everyone moans about the red. Maybe like a vibrant yellow.
Okay. All right, I'll have a bash at yellow and we can take it from there.
Okay.
Okay. Right, so let's go to the yellow. Let's try that one.
Yeah,
okay.
guys, let us know. I think yellow will be much
Let's see how yellow
better.
works. That looks a bit better.
Oh.
Okay. So guys, they'll be talking about the Newton meter. Now, I just want to extend the page slightly. There we go. Guys, the Newton meter is what we call the joule. Okay, and that's got a symbol that is given as capital J. Now guys, we must remember that joule, the name joule actually is named after someone, so we have to make sure that we do write it as a capital. Okay, and you might have heard about the joule being used as a unit for some other physical quantity. And a lot of you will probably be jumping up and down and saying, well, isn't that the unit of energy? Well, absolutely correct. So if the Newton meter is equal to the joule, and the unit of energy is also the joule, then there must be a direct relationship between work and energy. And this is exactly what today's lesson is all about, is that we are actually looking at basically a direct transformation in terms of work and energy. And the important thing to remember is that when work is done, we always say energy is transferred. Okay, and I'll put a box over that. There we go. When work is done, energy is transferred. Now guys, that is probably one of our most important concepts when it comes down to work and energy. That they actually are one and the same thing. So if I go back to my calculation, there it is. 1,000 joules, okay? I've got 1,000 joules. What does that mean? Well, 1,000 joules of work is done, which means that 1,000 joules is transferred into some form of energy. Now the big question is, what type of energy will it be transferred into? And I'm sure a lot of you will probably know the answer. It's kinetic. Kinetic energy. Now, what is kinetic energy? It's the energy due to motion or due to movement. And didn't I say that when a force is applied, the object must move in the direction of that force? Well, what's going to happen there is that when it moves, that motion is given into kinetic energy. Indiana, shall we take a little break?
Yes. Guys, let's take a little break, and then when we get back, hopefully Bruce will answer a few of your questions. I know we've got a lot to go through, so stay stuck to your seats, don't go anywhere, and we'll see you after the break. Welcome back, Matrix. I know that you're having a fab lesson. The questions are coming in. And you know what? Strangely enough, most of the questions that you've posted, Bruce is going to be getting onto shortly. I'm telling you, it's like you guys know what he's going to be speaking about. So Bruce, without further ado, let's get straight back to you.
Right. I'm going to be taking some questions now. So guys, hang on there. I just want to elaborate a little bit more about this concept of work done and energy transferred. And just before the break, I introduced the concept of the work being done, energy being transferred, where does that energy, what type of energy is being transferred to, and because it's moving, we said kinetic energy. So let's see now how we can take that same problem and how we can apply the kinetic energy to it. Okay, so what we did, was the work was equal to my force times delta x, and we had 100 newtons as my applied force. My displacement was 10 meters, and we came up with an answer of 1,000 joules. Now, if work done is equal to my energy transferred, and my energy transferred is equal to kinetic energy, I can make that very simple little statement there in front of you. And as you can see now, work is equal to EK. EK, my symbol for kinetic energy. Let's just extend the page slightly, and what we can see now, so therefore my kinetic energy in the system is going to be 1,000 joules, okay? And then what we can do is that we can work out now how fast that object is moving. Can you remember from grade 10, what was the formula to calculate kinetic energy? Now a lot of you guys will probably know the answer. We all know that EK is equal to a half mv squared. And there, guys, is now another little tool that we've got, another arrow in the quiver, that allows us now to work out the velocity of that object as a result of the work being done on it. So if I had to go and do the maths quickly, I could say, well, I know that my kinetic energy is 1,000 times a half. My mass was 100 kilograms. I think I didn't. Did I put a mass in here? I don't think I did. Hang on, let me just put a mass in there quickly for us. Let's say it's a mass of 10 kilograms. Just make it a bit easier. And if our mass is 10, and therefore it's going to be v squared, and therefore if I do the maths over here, 1,000 divided by, well, it will be 10, it will be over 5, will equal v squared, and therefore v squared, extend it a bit, v squared is equal to 200, and all we have to do is work out the square root of 200, which you can do on your calculators, and we will get a velocity which is the square root of 200 in velocity units of meters per second. Be careful here, guys, because remember, we are dealing with velocity, and velocity is a vector quantity. So what we should do is, when we've got our answer here, we should say to the right. Okay, because I had my motion moving to the right there. And therefore, we are complying with the vector requirement of velocity. Okay. Right, there's our relationship between work and energy. Indy, you had some questions? Do you want to fire those at me?
I did. Let's have a look. Okay. Now I'm trying to find them. You see, everyone keeps sending questions and it's going through. I know it's... What happens to energy when forces are acting at equilibrium? And that's from Anele.
Okay, when forces are acting at equilibrium, Anele, what's happening now is it means all the forces are balanced. Okay, will the object move if the forces are balanced? Now, to answer that, you might have to go back to grade 11 and think about Newton's laws a little bit. And I'll extend the page a little bit and we can just chat a little bit about that. And where's my pen over here? And I want to go to Newton's second law, which I'm going to call Newton 2. Okay. Now, you'll remember from Newton's second law that we developed a very famous equation. It was F net, which represents the net force, was the mass times acceleration. We've got a number of forces. We've got applied forces, we've got frictional forces, and we've got this thing called a net force. Okay. Now, the important thing about a net force is that a net force always produces acceleration. The object will accelerate. Okay. Now, how do we get a net force? Well, a net force is due to unbalanced forces in the system. So, for example, if I took my object like that, and let's say I had 100 newtons acting to the right, and then I had another force of, let's say, 50 newtons acting to the left, can you see now that we've got opposing forces? One is to the right, one is to the left. What will be the net, or often we use the word resultant force? Okay, now to work that out, okay, all we have to do is say F net is going to equal, and I'm going to call this F1 to the right, I'm going to make this one F2 to the left. I'm going to say all we have to do is use the little equation, F net is equal to the sum of all the forces in the system. So I've got F1 plus F2. But now before we jump in and put everything and substitute everything into that little formula, we must remember that forces again are vector quantities. In other words, they've got direction. So if I now have got direction, I'm going to choose a direction which I'm going to make to the right, I'm going to make positive. Which means now that anything acting to the left is going to be negative. So what's going to happen is that we are going to have F1, which is plus 100, plus F2, which is now minus 50. And can we see now that this works out to be 100 minus 50, and my net force is going to equal 50 newtons to the right. Okay. Now, that means that that object is going to accelerate, and therefore it's going to go faster and faster. If these two forces were the same, Anela, then if this was 100 newtons, then our net force is going to be 0. I hope you agree with me on that one. And if it's 0, is the object going to move? No, it's not. So there is there's no work done in the system to cause energy to be transferred into kinetic. However, what will happen is that the internal energy of that object will start to increase. Okay, we increase the internal energy. There's no motion, okay, therefore no work can be done. Therefore there can be no kinetic energy. However, we build up the internal energy of the system, and forces in equilibrium, that's what they do. They will just build up the internal energy of that object. Yeah,
that's amazing. Okay, let's have a look. There's quite a few. So Bruce, what happens when the work is done on an inclined plate? How do we draw?
Plane.
Plane.
Yes.
Inclined plane, Bali.
Yes.
See, she's making me look silly here now. And how do we draw the free body diagram of it, please?
Okay, we're going to be looking at inclined planes a little bit later.
Okay, that's fine, Bruce. You must just
All
tell
right.
me if that happens.
We're probably towards the end of this lesson, we'll look at inclined planes. So I'll wait for that question. We can ask that question a little bit later.
Bali, make sure that you are watching for later. Let's see if there's one more that we can go over before you move on. There's something that I want to quickly go over is, if you can go over quickly, Noxipedia said, what do we exactly mean by vector quantity?
Okay.
And what I love about this, Bruce, is that if you guys' mindset is go and have a look on the page, go and see Noxipedia's comment, and you'll see that there have been other mindsets that have answered it for us. But I mean, I'd like you to go through it to see if they're right.
Guys, when it comes to quantities, measurements, and things like that, we have two types of quantities. We have what is called a scalar quantity and something we call a vector quantity. Okay. Now, you guys sitting in grade 12, you probably would have had this introduced to you in grade 10, definitely in grade 11. So I'm hoping that this will be pretty much a revision exercise for everyone. A scalar quantity is a quantity that does not have any direction. It's got magnitude, yes, we can measure it, but it does not have direction. A vector quantity, on the other hand, has got magnitude, but it's also got a direction. Now, I'm going to do a very short example just to make sure that we do understand it. If I'm starting at point, whoopsie, let's get this pen up. If I'm starting at point A, okay, and here is point B over there, okay. Now, I'm going to move, I'm going to pretend I'm in a car and I'm going to drive from point A to point B, and I'm going to jump in the car, and I'm going to take off. I'm going to climb a couple of hills, take a few left and right turns, and what's going to happen is that, boom, I'm going to arrive at point B. Can you see now that I have traveled a certain distance, and I've followed the route length, or let's call it the path, okay, from point A to point B. So, for example, if I was going to Durban to Joburg, I would jump on the N3, and off I'd go from Durban to Joburg, and I'd follow the road. Okay. However, if I actually was in an aeroplane, what I probably could do, in fact, I'm going to do this in a line here. No, it's not going to work. If I was in an aeroplane, I could actually take off in the aeroplane from point A, and I could go in a straight line all the way to point B like that. Now, can you see that I can measure the path length from point A to point B? But can you see now that I have got a specific direction that I have traveled from point A directly to point B? So therefore, what we call this is our displacement. Okay, that's a displacement. This sort of roundabout way here, this path here, is called a distance. Sorry, I'm just going to grab some water quickly.
That's okay. While you're having a sip of water, Pusaletso wants to know what happens when the force and displacement are at an angle to each other, as opposed to the squiggly. Would it be the same?
Yeah, and what I'm going to do straight after this, I'm going to look what happens when we have force at an angle and how work is calculated with forces at an angle.
Okay.
So okay.
Perfect. Fantastic.
But I just want to quickly finish this one off. So can you see now that the path length is the actual distance? There's no real direction. It's all over the place. It's up, down, over the hills, left and right turns. So this now is what we call, oopsie, let's get this, sorry. This is what we call a scalar quantity. Okay, so distance is going to be a scalar quantity. When we go in a straight line from A to B, that is what we call a vector. Okay. I'm sorry, I think my cold sort of got my throat a little bit, but I'm getting through it, so don't worry guys, I'll make it, don't worry. So there now is my vector quantity. Displacement has got magnitude. I can measure from A to B, yes, no problem. But it's got a direct direction from A to B, that what makes it a vector. Okay.
Fantastic. Cool beans.
Right, and I think we wanted to chat a little bit about those angles, eh?
Yeah, should we?
Right, I just want to scroll that down. In fact, let me just get a new page up. And so give me a little bit more space. Now, guys, there's been a couple of questions. Is what happens now if the force that's acting on the object acts at an angle to that object? So I'm going to draw exactly the same. I'm going to draw exactly the same diagram, but notice now, guys, I have not put my applied force in the same straight line or parallel to the direction of motion. I have now drawn it at an angle, which I'm going to just mark in like this, at an angle theta to the horizontal. The important thing, guys, is that the word I use there is absolutely crucial. I have drawn in the angle theta to the horizontal, which means, guys, is that although my force is acting at an angle, the object is still going to move horizontally, which means, guys, I have to now use what is called a horizontal component. I have to use what is called a horizontal component. Now, again, we're calling on your knowledge of grade 11, because when you guys did forces in grade 11, you would have been told about how we resolve forces into components. We have two types of components. We have got vertical components, okay, which I'm going to draw in like that, and we've got horizontal components. So I'm going to do it like this. I'm going to call that VC. I'm going to call that HC. Now, all a component is basically two forces, in this case forces, at 90 degrees to each other that represent the combination of the force, the 100 Newton force at that angle. So what we have to do now is somehow be able to calculate the horizontal component. We are not interested in the vertical component. Very importantly, and the question comes up, why don't we include the vertical component here? Because, guys, the force must act in the direction of the motion. Okay, and work is only done if the force is parallel to the direction of motion. The vertical component is not in the direction of motion. In other words, can you see now that the vertical component is at 90 degrees to the direction of motion? And any force acting at 90 degrees to the direction of motion cannot result in work being done. Okay, and I'll say that again because it's also a very important part of physics here. Any force acting at 90 degrees to the direction of motion, no work can be done by that force. Okay, we have to make sure that our force is parallel to that direction of motion. Which means, guys, is that over here, we have to now calculate our horizontal component. And the big question is, how do we calculate that horizontal component? And here now, guys, a little bit of math skill starts coming in. And what we're going to look at is a little bit of trigonometry. So, what I'm going to do...
Nguako, you are so right. He already said, are you going to be tackling trigonometry?
Okay, right. There now is my force, my 100 Newton force. There's my angle theta. So I'm going to write it in, 100 newtons. Now, what I'm going to do for trig is that I'm going to take that vertical component and I'm going to complete the triangle here. Like that. In other words, that's my vertical component there. This is my horizontal component over here. Now, with trigonometry, what do we need to do? We need to label the sides of that triangle. Remember, guys, it has to be a right-angled triangle. And yes, we have a 90 degrees between vertical and horizontal. So we've got our 90 degrees, our right-angled triangle there. We've got an angle theta, which is the angle between the horizontal and the applied force. So this now becomes known as the opposite side. This now becomes known as the adjacent side. And you'll all tell me now that, whoops, that the other side becomes known as the hypotenuse. Okay. Now, if this is the adjacent side, in other words, the adjacent represents the horizontal component, and we know the value of the hypotenuse, what trigonometric function is going to allow us to include the adjacent in the calculation? And hopefully all you guys are jumping up and saying the cos function, cosine. So cos theta, okay, is going to equal adjacent over hypotenuse. Okay. Now, what does that mean? Well, if it's adjacent over hypotenuse, the adjacent represents the horizontal component. So I'm going to call it, whoops, the pen's just not behaving too well at the moment. There we go. I'm going to call that FHC, the force of the horizontal component, or should we rather say horizontal component of the force, which is going to equal the hypotenuse, which is the applied force multiplied by cos theta. And there, guys, is how we calculate, so that's an A over here, that is how we calculate the magnitude or the value of the horizontal component of the force when the applied force is acting at an angle on that object. So, let's have a look at a problem. Let's do a problem together, and let's see what we can do. So, let's scroll a little bit here. Things not moving too much. There we go. Right, so what I've got a little problem here to do with you guys. And what I'm going to do is take my object. I'm going to put in my 100 Newton force there. And I'm going to make this a 60-degree angle. Okay? The object is going to move. Displacement is going to be 10 meters. Okay? And let's see how we do it. Well, here we go. We've got a 60-degree angle. We know that the work done is going to equal the force multiplied by the displacement that's going to be covered. Okay? But because we're now at an angle, we have to now use my horizontal component. So I'm going to put there HC times my displacement. Right, let's work out my horizontal component. So it'll be, HC is going to be F applied times cos 60, which is going to equal 100 times cos 60. And cos 60 we all know is 0.5. And therefore, we're going to find that my horizontal component is going to equal 50 newtons to the right. Okay, again, I'm keeping compliant with my vector quantity. Force is a vector quantity. I must put in my magnitude and direction. Now, simply substitute that in over here, and what do we get? We get 50 times, where we're going, delta x is 10, and can you see now that we are now having, the amount of work is going to be 500 joules. Now guys, I've used exactly the same values that I did with my previous question, and we know that the previous question came out to be 1,000 joules. So can you see now, by having an angle of 60 degrees, the amount of work done on that object has actually dropped by half. We've only got 500 joules of work. So therefore, where does that work go? That work is going to be transferred into kinetic energy. And the kinetic energy is then going to cause that object to move at constant velocity. Okay? And if it moves at constant velocity, then we know that work done is equal to the gain in kinetic energy, and therefore the work done, which was 500 joules, is going to be a half mv squared, and therefore substituting in 500 equals a half times the mass, and we made the mass, sorry, there was 10 kilograms, times v squared. So that's going to be v squared will equal, divide by 5, 100, and very simply to square root 100 would be 10 meters per second to the right. And there, guys, is how we can work out the velocity of that object. Any more questions, or are we going to take a break?
You know what? We've got so many questions, but I think after that question, we're all going to take a break. I'm going to give Bruce some time to have a sip of water. You guys do the same, and we'll be back with you in literally 2 minutes. See you then. Hi Mindsetters, grade 12s, welcome back. Can you believe that we've only got 15 minutes left to this lesson? I can't, it's just gone so fast. Guys, I just wanted to let you know that we are giving away a Casio calculator in today's lesson. We will be contacting the winner after the show, so keep those comments coming in. I'm not looking for anything in particular today. I'm looking for mindsetters that help each other out. Post those comments. Let us know what you're struggling with. We've only got about 15 minutes left, so let's get back to Bruce and let's have some fun. Bruce, are you ready?
All right, good.
Cool.
Well, guys, welcome back after the break. And one other thing I wanted to have a chat about before the end of today's show is going to be having a look at friction. Now, at the moment, I've been talking about frictionless surfaces. We've spoken about the forces acting in the direction parallel to the direction of motion, therefore causing work to happen. And we've also looked at the applied force at an angle on the object, but then we're having to calculate the horizontal component. But what happens now if we have friction? We bring friction into the entire problem. Again, last year, grade 11, you'll remember that when we did Newton's laws, we also looked at bringing friction into the whole equation. How do we do that now when it comes to work? Well, it's very simple. What I'm going to do is draw on my block. Here's my 10 kilogram block. Okay, I'm going to keep this now in the horizontal plane. Okay, and I'm going to now introduce a force of friction. Okay, and we must remember, guys, that friction is a force that always acts in the opposite direction to the direction of motion. So if I've got my applied force acting in this direction, okay, then the applied force is going to cause the object to move, then my friction must be acting to the left. And that becomes very significant because, again, we're introducing that vector part or the vector considerations into these type of calculations. Again, so what I do is to make life simple for me. As soon as I get friction or something acting in the opposite direction, I like just to put in my arrows to remind me which direction I'm taking is positive and which direction I'm taking is negative. Personal preference, I do like to make to the right going to be my positive. Now, guys, let's have a look. There I've got 100 newtons, okay, and 100 newtons acting to the right. Now, this object, I'm going to tell you, is moving with constant velocity. Okay. Now, we had a little Twitter question, or it was a Facebook question a bit earlier, where we said if the object moves at constant velocity, then the forces in the system are in equilibrium. They are balanced. So straight away, what you should be able to tell me now, that if the object is moving at constant velocity, okay, so yes, work is being done because the object is moving to the right. What is going to be the magnitude of my friction? Well, if the forces are in equilibrium, then my applied force must be equal to my frictional force. Okay, which means then that the object is going to have work done due to the applied force as well as work done against the motion, because it is moving, so work done against the motion, the work done due to the frictional force. And therefore what we can introduce is what is called applied work, okay, which is going to be the work done due to the applied force times the displacement, okay, and then we can have the work done due to the frictional force, which is work, little f, which is frictional work, which is the work done due to the frictional force multiplied by the displacement that the object is covering and experiencing that frictional force. So guys, we are now introducing different types of work into the system. The applied work, okay, and the frictional work, okay. Now, what happens, okay, if we have this? Let's extend it one more. There we go. Let's take my object, okay. Let's put the object onto a different surface. In other words, there's my 100 newtons acting to the right. I'm going to change my surface, and my frictional force is now only going to be 20 newtons. Okay. Can you see now that my applied force is right in there? Oh, goodness. It's jumping around a bit. My apologies. My applied force, which is equal to 100 newtons, okay, to the right. Our frictional force of only 20 newtons to the left. Can you see now we do not have an equilibrium? The forces are not balanced. Now, remember I used it earlier on in the show. What do we call a force that is not balanced? Well, an unbalanced force is known as a resultant or net force. And how do we calculate that? Well, we have a net force. Is simply adding the forces in the system together. So it'll be F applied plus the frictional force, which is going to equal, well, remember, to the right we're making positive, to the left we're making negative, okay? So it's going to be plus 100 plus minus 20. Whoopsie, I nearly put down 50, my mistake there. Sorry, let's rub that out. Bring back the pen, here we go. Plus minus 20, which, quick maths, 100 minus 20, we have got a resultant force of 80 newtons, or a net force of 80 newtons to the right. Okay. Now, remember guys, what do net forces do? Net forces cause acceleration. So this object is now going to accelerate. Okay. Which means then that the work done, okay, is going to be due to now what's called a net amount of work. Okay, so what we're going to have is W net. The net amount of work is going to be due to the net force multiplied by the displacement that the object covers. And now we've introduced what we call a network. And this introduces something that is going to be almost 100% guaranteed to come up in your exam at the end of the year. And that is known as the work energy theorem. The work energy theorem. Okay.
You know, Bruce, these mind-setters they get, I mean, I've gotten Bailey on here, and she's saying to me that, you know, she gets there's so many terminologies that she has to learn. I mean, how do they learn these terminologies? The best thing is to write them down, I suppose, and learn them off by heart.
Indiana, two ways. Okay. Number one is to sit down, write them down, learn them as definitions.
Yeah.
You're going to be asked definitions in the end of your exam. The next one, and I think is probably the more important, is to practice problems that involve all these different types of work dones and things like that. So we've got applied works, we've got frictional works, we've got networks and things like that.
Yeah,
and
exactly.
The work energy theorem is actually a very important theorem that allows us to look at the network within the system. Because, guys, network is calculated through a net force. A net force produces acceleration. Now, what happens if an object accelerates? Well, the velocity is going to change. So, therefore, what we're introducing now, if the velocity changes, then the kinetic energy is going to change. So, if I have an object over here, okay, and it moves to this point over there, let's call that point A, and this point B, okay, and let's say it had a velocity of 10 meters per second, and over here it's got a velocity of 15 meters per second. Straight away, guys, can you see now, for the velocity to change from 10 meters per second to 15 meters per second, we must have had a net amount of work, or a resultant force, should I rather say, acting on that object. The resultant force has produced the acceleration, and therefore the resultant force has caused the velocity to increase. So, if we had to look at the EK here, which is a half mv squared at that position, and a half mv squared at that position, I'm going to call that EK initial, I'm going to call this EK final, okay? Can you see now we've got two kinetic energies, which means then we have got what is called delta EK, a change in kinetic energy. Now, what does the change in kinetic energy equal? Well, it must equal the net work done. And that is one of the very important components in our section on work. It's called the work energy theorem. That the net work done as a result of the net force in the system is going to cause a change in kinetic energy. And this change in kinetic energy allows us to do the net work. So, for example, if this was a 5 kg object, okay, we could very simply work out the initial kinetic energy because we've got mass and we've got velocity. The final kinetic energy, because we've still got the mass, that hasn't changed, times the velocity. And then delta EK, and very important, is always your EK final minus your EK initial. And that delta EK will equal the net work done in the system. And from there, extend the page. I know it's very theoretical at the moment, but we know that W net is equal to the net force times delta X. Okay. From there, we can then calculate the net force, and from Newton's second law, F net equals ma, we can actually calculate the acceleration. Can you see, guys, it's a bit of a sequence of calculations, a bit of a sequence of mathematical equations here. And that is why the examiners love this type of question, because they can now start adding all sorts of things to it. So ultimately, what we've got to try and do in our next show on work is to actually do problems, do some examples associated with the work energy theorem. And once we can do that, then we'll be able to practice these and see how this whole thing works. Okay. Anything else on Twitter and Facebook?
Twitter and Facebook, Bruce, there are a few. Okay, I know the producer said we've got about 3 minutes.
Okay.
So let's get through them. And I see Lebza, I see you're getting there. She was a bit confused, but now she's understanding. Go, girl.
Okay.
Okay, let's have a look. Let's see, over here. Sure, there's so many questions. Okay, this one's from Nguako. He said, total work done by an object is equal to change in kinetic energy of an object. That law is expressed mathematically by this equation. W net equals EK.
Delta EK.
Delta EK.
Yeah.
And is that correct?
Yeah, it's the network. Remember, so what was the guy's name?
This is Nguako.
Nguako, remember that if your kinetic energy changes due to a change in velocity, okay, then you've got this resultant or net force. And a net force always produces an acceleration, either a positive acceleration to make the object go faster or a negative acceleration to make it go slower. Okay, so in Nguako, just realize that when we have this change in kinetic energy, we're looking at what's called the net work done, because the net work done is directly as a result of the net force that's in the system, that's creating this change in kinetic energy. Okay. I'm sure that'll help.
Fantastic.
Yeah.
Okay, and Bunny wants to know, what is a non-zero resultant force?
A non-zero resultant force. Well, a zero resultant force is a resultant force that is zero. Now, what does that mean? That means that your forces are in equilibrium. Your forces are balanced. So are you going to have acceleration in a balanced system? Absolutely not. That object will either remain at rest or will move with constant velocity. No change in velocity at all. Okay. A non-zero resultant force means that your resultant force is greater than 1. And if anything is greater than 1, therefore the forces are unbalanced, and therefore we must have an acceleration taking place. If it's an acceleration, then you're going to have a change in velocity. A change in velocity, a change in kinetic energy, then you must have a net amount of work done in the system.
Fantastic. Okay, so I think, guys, that has led us to the end of our show. Guys, don't forget that we are giving away this Casio calculator. Unfortunately, we're not going to announce it now, but we will be announcing it on the Facebook page straight after the show. Thank you so much, guys. And like you said, Noxie, PDA, you know you, she said she cannot believe that time is finished, but unfortunately, grade 12s, we have to say goodbye to you. But you know what? We will be back next week. And we will see you another 20 seconds, my producer's telling me. Oh, gosh. Okay, guys, thank you so much for joining us on Facebook and Twitter. You guys are fantastic. After the session, please go and help each other out. I know there's a whole bunch of them. It's fantastic. Bruce, it really is when they help each other out on the page.
Cool. No, that's great.
Yeah. Guys, we are a community of mindsetters. We're not doing it alone. We're doing it together. And I think that that's absolutely fab. And I hope you've all had a fantastic, fantastic Valentine's Day and all loving each other a lot. Grade 12s, mindsetters, thank you so much. And we'll see you next week. Bye.